Hello everyone, my name is Pratik Savle and today I will be presenting one of the most fascinating topic in the deep learning, that is diffusion model. So let us begin. With why. Now diffusion models are a class of latent variable generative model that can generate realistic synthetic data like images, text, or audio, or even videos. Now they are inspired by a principle of non-equilibrium thermodynamics, which means they can simulate a gradual diffusion process to model data distribution. Unlike other models that don't rely on adversarial training, so they are more stable, more diverse in what they produce. Now, why do you even need them? The goal of generative AI is to produce new data that looks real, not synthetic, whether it's picture, whether it's audio, or even video. Older models like generative adversarial network and variation network encoders were groundbreaking, but they were imperfect. They faced problems like training instability, mode collapse, where output lose diversity, and a quality diversity trade-off. Diffusion models overcome these issues. They powered applications like DEL-E for image generation, audio synthesis, or even protein structure prediction in biology, showing their versatile across all domains. The main idea of diffusion model is simple but yet powerful. The idea is to start with real image, then gradually add random noise until it turns into pure noise. That's called forward diffusion process. Then the model learns to reverse this process step by step by removing the noise to reconstruct the original data. Once trained, it can start from pure noise and generate a brand new image that looks completely real. In essence, diffusion models learn how to turn noise into creativity. The key components of the diffusion model are the forward process that add noise, the reverse process that removes it, and the noise scheduler that decides how much noise to add or remove at each time step. In forward process, noise is added to the data over several steps, kind of like watching a clean picture slowly getting covered by a static. This process can be described mathematically, but conceptually, it's just a gradual degradation of a data using Gaussian noise. The goal is to simulate randomness until the data becomes indistinguishable from the noise. Now comes the exciting part, the reverse process. Here the model learns to undo all the noise step by step by predicting what noise was added to each stage. A neural network learns to generate denoised output and over many steps. The model reconstructs the original data or even creates something entirely new. This is how models like diffusion generates probabilistic image from a random noise vector. During training, the model learns to predict the noise added at each step of the forward process. This is done by minimizing a loss function that measures the difference between predicted and actual noise. Let's look at how forward diffusion process works. This process involves gradually corrupting the original data denoted by x0 by adding Gaussian noise over several time steps. We represent the noisy data at each time step t as xt. Mathematically, this process can be represented by this formula. Here, beta t is a noise schedule that controls how much noise to add at each time step, and epsilon represents the Gaussian noise. At the time step t increases, more and more noise is added, and eventually xt becomes nearly pure Gaussian noise. So forward process is basically turning a clear image into contained random noise. And the model's job is to learn how to reverse this process to bring back meaningful data. Now the reverse process, in which where the actual generation happens. In these steps, the model tries to undo the noise that were added earlier, gradually converting random noise into structured realistic data. Mathematically, it can be represented by this formula, where mu naught and sigma theta are parameters learned by the neural network. They determine how much noise should be removed at each time step. In simple terms, the model learns to predict noise that were added at each time step in forward process. Over many such denoising steps, the system slowly reconstructs the original data, or even generates a completely new and realistic image. This reverse process is what makes diffusion models so powerful that they don't just reproduce data, they can generate entirely new samples that look real more than synthetic data. During training, the model is trained to predict the noise added during forward process and denoise it in a reverse process. Now, this is done by minimizing the loss function. Basically, loss function means it measures how close is the predicted output to the actual output. The loss function is typically mean squared error between these two quantities, which is given by this formula. This encourages the model to accurately predict the noise and consequently denoise effectively during the reverse process. Like any other model, diffusion model also has some drawbacks. It is not totally perfect. The several key drawbacks include it has slow sampling, means generating an image requires hundreds or thousands of sequential steps, making it 10 to 100 times slower than generative adversarial network. It has also high computational cost, means training large diffusion models can take over thousands of GPU hours, that is lot of energy at a time. And it has also hyperparameter sensitivity, means the noise schedule and step size need to be carefully tuned, otherwise model will be unstable or not reliable. For example, generating one image on a regular consumer GPU can take around 20 seconds to 30 seconds, which limits their use in real world applications like interactive art or live video generation. Now, to sum up, diffusion models are reliable and mathematically grounded generative models that transform random noise into meaningful structured data, literally turning noise into creativity. They have proven their impact through models like DEL-E, which have revolutionized AI-generated content. Although computationally expensive, newer variants like latent diffusion or DDIM are making them faster and more efficient. So, diffusion models are truly represent next era of generative AI, where mathematics meets imagination. Thank you, guys.